As many of you know, a couple of the senior engineers at my workplace have departed in the past 12 months with a combined 97 years of experience in the building between them. And so they've left behind a lot of interesting parts for us to sort through. And these are a couple of them. These, as you can probably tell from the label, are the Sigma Datacel Series 301. Um, and these don't exist on the internet. Now, before you rush to the comments and tell me just how wrong I am, yes, these do exist on a couple of new old stock websites for repairing things like apparently antique radios and various things. And on those sites, they are described as optical relays or soft switch optical relays or something like that. But I have not been able to turn up a data sheet for either of these. But from the pinout diagrams on the side, we can see that rather than using an LED and a photodiode like a modern opto-isolator would, these actually use a physical lamp and some light dependent resistors to provide a level of isolation between a pair of circuits. So this is the 301R4 with 4 light dependent resistors in there. This is the 301R2 with 2 resistors. That makes good sense. The antiqueradio.com forum speculates that the dash 24 means that this is a 24 volt lamp, which seems plausible, so we'll start with that. Thankfully, in our collection from our departed engineers, we also had a couple of these sockets, which are made just perfect for the weird pinout on the bottom of these pins. And I've already gone ahead and wired it into a breadboard so we can experiment with it. So we'll play around with it a little bit, and then we'll take one of these apart and see what they look like inside. With a couple DuPont wires here, I've now got this hooked up to my DC power supply. Oh, you can see me in the reflection of the power supply. Hello. Let's turn the voltage all the way down. We'll turn the current limit up. So we'll do this in sort of a voltage controlled mode. And we'll just start dialing up the voltage on this power supply until we start to see a drop in resistance. At some point, it looks like the resistor in pins 5 and 6 in here is actually perhaps defective or dead. I could not get this to go below 10 mega ohms on any voltage. But after a little off-camera testing, if we switch over to another one of those light-dependent resistors on pins 7 and 8, there we go. We can see that at about 3 volts or so, 3.5 volts, that lamp inside must start to light, and we start driving the resistance on those light-dependent resistors down. So already at 5 volts on what is nominally, I'm sure, a 24-volt lamp, we're down to 5 kilo ohms. And as we increase toward 12 volts here, just as an arbitrary stopping point, we're down to 310-ish ohms, and we'll go up to our what I'm going to guess is our nominal lamp voltage of 24 volts, something like that, and we're down to about 80 ohms. So that's the essential function of this, right? There's a presumably 24 volt lamp inside here, 4 light dependent resistors, or I would guess 2 for the R2 version of things, and as you apply voltage across that lamp, the resistance on those resistors changes. So an optical isolator using light-dependent resistors. So that's what it does. Let's see if we can get a look inside of it. So this looks, I'm going to take apart one of the 2 resistor versions because I have a lot more of these access to, and it looks like this metal can is just sort of crimped around this plastic base. So let's use the wrong tool and just see if we can sort of prise that open there. Yeah, there we go. There's 1, 2 crimps. There's actually a little metal tab. I don't know if you can see it there. Just poking out. I'll bet that's where some of the internals are sort of making contact with this shield. You can actually see, I believe that this pin 5 here is meant to indicate that that's like the chassis ground of this circuit. We'll see if that's true when we get inside. If this pin here is actually what's connected to that tab there. So we'll open up tab 3 and tab 4. I'm going to see if this thing will just come open. Ooh, I heard something snap just there. I hope I didn't bust part of this before we get inside. All right. So that metal cover just came right off. And inside, what have we got? So there are 2, I feel like, plastic bits around the side. And then this is interesting. This is like a gel, a sticky gel. I mean, maybe it's not sticky. It's like it feels, in consistency, it feels like credit card goop, right? The stuff that sticks your gift cards to the inside of your gift card package. There's only adhesive to the plastic there. And well, that's interesting. So there's obviously our bulb, right? That's our 24-volt lamp. But where? So that must have been in this orientation. Where are the resistors? Oh, there they are. Ah, okay. So this is not two pieces of plastic on the outside. Look at this. This is two, well, maybe carbon resistors, and they're attached to those two outer pins at either end. I don't know what the mechanism of this is, but clearly as these are heated up directly by the ambient heat of that lamp, the resistance goes down. That's fascinating. Well, I think we're going to have to do something where we're going to have to hook this up to power with it open just to see what happens. So here's our Sigma R3 back in our socket, wired up again to our power supply. And if we turn the voltage up here, we should start to see those filaments glow. Hey, there we go. All right, let me turn the ambient lighting down here just a little bit so we can see that better. And as we turn this up to about 24 volts, we can see, I mean, it really is just an incandescent light bulb inside of a container. I'm curious if I were to take the cover and sort of slip it back on, would the resistance continue to decrease? Because presumably a lot of that heat that would normally be captured inside of this enclosure, and with this, maybe heat-resistant gel substance that was in there, which of course I can't get anything to focus on, but a lot more heat's escaping. I'll bet the resistance is higher. Now, I realize that we're comparing measurements here on the R2 versus the R4 version, which have different baseline resistances, so it's not going to be a perfect comparison to the earlier measurement we took, but I think what we can do is just sort of put this cover back in place and see how the resistance changes when we introduce more heat into the equation. So as I trap that heat in there and this heats up, now we see sort of our stable resistance. It's funny, if I put my hands around it and sort of help trap a little more heat, the resistance continues to drop. And if I pop that back off and let some of that hot air back out, let things cool just a little bit better, the resistance drops. Although not nearly so much as I would have expected. I mean, I guess the resistive parts of this circuit are right next to that bulb, so the ambient air temperature isn't a huge factor as much as sort of the radiant heat of that light bulb. I wonder, so I've kind of destroyed this little gelatin thing by taking it out, but maybe I can sort of piece that back in here as well. We can see how that responds. That's just kind of laying on top of the light bulb there. We'll trap that in. That might just be heat protection so the top of this doesn't get super duper hot. So yeah, so maybe a little bit more heat trapped, not a huge amount. Again, down about 40 ohms with the cover on and like 45 ohms with the cover off. So that's the Sigma Datacel soft relay thing that I found. So like I say, I'm claiming right now that the datasheet for this does not exist anywhere on the internet, which by the laws of internet, I think means that someone has found it right now and is putting it in the comments. If they have, I will certainly put a link in the description or any other interesting info that folks find. Anyway, just a bit of a nerd diversion. Have a wonderful day.